Paging, smaller tables. We now tackle the second problem that paging introduces. Pa- Page tables are too big and thus consume too much memory. So the page table is too big, that's why we use TLB, and thus we need to better manage the page table. So again, page table is just a data structure. We will try to create a better data structure and algorithm to manage it. As you might recall, we can also use hardware to manage it, but a software manage is more flexible. As you might recall, linear page tables get pretty big. Assume again a 32-bit address space, 2 raised to 32 bytes, with 4 kilobytes, 2 raised to 12 bytes pages, and a 4-byte page table entry. An address space thus has roughly 1 million virtual pages in it. So 2 raised to 32 over 2 raised to 12. Multiply by the page table entry size, and you see that our page table size is 4 MB in size. So that's 1 million virtual pages multiplied by its page entry, which gets our page table as 4 millibytes in size. Recall also, we usually have one page table for every process in the system. So we allocate page table for every process in the system. With 100 active processes, not uncommon on a modern system, we will be allocating hundreds of megabytes of memory just for page tables. So 100 MB just for translation for page table. If in case that we have a process that gets a lot of memory, such as normal for 100 processes, like including daemon applications, common applications such as Word files. So none of them can be handled by TLB, right? So we need a better way to handle page table. As a result, we are in search of some techniques to reduce this heavy burden. How to make page tables smaller? Simple array-based page tables, usually called linear page tables, are too big, taking up far too much memory on typical systems. How can we make page tables smaller? What are the key ideas? What inefficiencies arise as a result of these new data structures? So a linear page table, which is an array data structure, take up far too much memory. So how can we create a better data structure? How can we make page tables smaller? So how can we make that data structure smaller? What are the key ideas? What inefficiencies arise as a result of this new data structure? Simple solution: bigger pages. We could reduce the size of the page table in one simple way. Use bigger pages. So a bigger pages, as we have learned, will lessen the TLB miss. That's why it will reduce the requirements for a bigger page table. Take our 32-bit address space again, but this time assume 16 kilobytes pages. We would thus have an 18-bit VPN plus a 14-bit offset. Assuming the same size for each PTE, 4 bytes, we now have 2 raised to 18 entries in our linear page table, and thus a total size of 1 MB per page table. So instead of 4 MB, we now have 1 MB because we could quadruple the size of our page as well. A factor of 4 reduction in size of the page table. Not surprisingly, the reduction exactly mirrors the factor of 4 increases in page sizes. The major problem with this approach, however, is that big pages led to a waste within each page, a problem known as internal fragmentation. So the problem with this is that when you have a big pages, though uh, big physical frame pages, you will have a lot of unused or internal fragmentation, kind of like in internal fragmentation we encounter in the first virtual form of memory for allocating the heap, the space between heap and the code. As the waste is internal to the unit of allocation. So again, the reason why it's internal fragmentation, because the waste is internal to the unit of allocation, because you allocated that to specific page in the first place, and a page is a fixed size, right? So it has the same size, so we cannot get that allocated space from that fixed size once we allocated it. Applications thus end up allocating pages but only using little bits and pieces of each. So now applications allocate pages but only using or utilizing the small bits or little bits of that page table entry we activated using the software and hardware in the previous video. Again, applications thus end up allocating but only using little bits and pieces of each, and memory quickly fills up with these overly large pages. Thus, most systems use relatively small page sizes, in the common case 4 kilobytes, as in x86 or 8 kilobytes. So because of this, most systems use fixed or 4 kilobytes, just enough to get the balance of the size so that it doesn't allocate or doesn't have this internal fragmentation as much, while at the same time providing this fixed page sizes and therefore supporting the TLB cache of modern CPU. So in x86 or 8 kilobytes in Spark version 9. Aside, multiple page sizes. As an aside, do note that many architecture, MIPS, Spark, x86 to 64, now support multiple page sizes. So they support multiple page sizes. So some large pages are for large process or large programs such as database management, and for the small page size is for the normal process. Usually a small 4 kilobytes or 8 kilobytes page size is used. However, so usually the division of these multiple pages are 4 kilobytes and 8 kilobytes. So these 8 kilobytes are for large process such as database. However, if a smart application requests it, a single large space of size 4 MB can be used for a specific portion of the address space. Again, if a smart application requests it, a single large space, a single if a smart application requests it, a single large space like a size 4 MB can be used. So actually, it's dynamic. If a large application requests for a 4 millibytes, that's not 8 kilobytes, it's 4 millibytes, it can be used for a specific portion of the address space. So it can cut a large portion of that address space for that alone, enabling such application to place a frequently used and large data structure in such a space while consuming only a single TLB entry. So again, we only have single TLB entry for each page. So this allocating that much space for a most common, kind of like making it a cache, is a normal for multi-page system. This type of large page usage is common in a database management systems and other high-end commercial applications. The main reason for multiple page sizes is not to save page table space. However, it is to reduce pressure on the TLB. So the reason for these multiples of size is not to save page table space, because again, the larger our pages, the larger our page table is. Sorry, I mean, just because the larger the page we have will make the page table smaller, does not mean that that is the purpose of this large pages. The purpose of this is to reduce the pressure on the TLB, enabling a program to access more of its address space without suffering from too many TLB misses. So it doesn't, again, we start with TLB and then access the page table. But in this case, you don't need as much TLB because the page table are huge enough to support that program in the first place, because a large of TLB misses, because database have a lot of random requests. So for that random request, you won't want that to be slow, because that's not a repeated request. Does not mean you won't serve that. For example, a database. So for a database that you used on your website, like a Firestore or Firebase, this is actually what they use, a large page table. However, as researchers have shown, using multiple page sizes make the OS virtual memory manager notably more complex. Or this virtual management or virtual form makes it more complex if you have a large table, and thus large pages are sometimes most easily used simply by exporting a new interface to applications to request large pages directly. So because of it is complex, it does large pages are sometimes most easily used by exporting a new interface to applications to request large pages directly. So it just provide the interface to that application requesting that large page instead of providing an entire large page for that process. Kind of like in a different app. It's easier to request that in a different app for them to abstract the complexity of allocating that large space in your operating system. Hybrid approach, paging and segments. Oh my god. Years ago, creator of Multics, in particular Jack Dennis, chanced upon such an idea in the construction of the Multics virtual memory system. So this hybrid came from Multics. So whenever we have these benefits from two seemingly different approach or techniques, think about ways to combine them, such as this a hybrid approach, because more often it can solve the problem. You don't have to choose which is which, but rather combine their pros. Specifically, Dennis had the idea of combining paging and segmentation in order to reduce the memory overhead of page tables. So since we have this internal fragmentation with large page table, So we also encountered that in segmentation, in a previous virtual form, and we use segmentation to solve that unallocated space. So why not use the same idea here that segmentation provides in order to reduce the memory overhead of page tables, or in order to reduce that requirements or unallocated space or free space. We can see why this might work by examining a linear page table in more detail. Assume we have an address space in which the used portions of the heap and stock are small. For example, we use a tiny 16 kilobytes address space with 1 kilobytes pages, figure 20.1. A 16 kilobytes address space with 1 kilobytes pages. The page table for this address space is in figure 20.2. So as you can see, only a little bit are used in this whole address space, and only a little are allocated. So for stock, you have 2-bit heap 1, code 1. So how do you deal about that? So you have a lot of non-contiguous memory. So here's what it is. In virtual 0, you have physical frame number 10, VPN 23. You have physical frame number 4, and then for 28.22, and then for 4, that's 27. So this example assumes the single code page VPN 0 is mapped to physical page 10, the single heap page VPN 4 to physical page 23, and the two stock pages at the other end of the address space VPNs 14 and 15 are mapped to physical pages 24 and 4 respectively. As you can see from the picture, most of the page table is unused, full of invalid entries. What a waste! And this is for a tiny 60 kilobytes address space. Imagine the page table of a 32-bit address space and all the potential wasted space in there. Actually, don't imagine such a thing. It's far too gruesome. Thus, our hybrid approach, instead of having a single page table or large page table for the entire address space of the process, or instead of having just one single table, why not have one per logical segment? In this example, we might thus have 3 page tables, one for the code, heap, and stock parts of the address space. Just a moment. Thus, our hybrid approach, instead of having a single now remember, with segmentation, we have base register that told us where each segment live in physical memory. So the base register in our earlier virtual form tell us where the virtual is placed in physical memory, and a bound or limit register that told us the size of said segment. In our hybrid, we still have those structures in the MMU. Here, we use the base not to point to the segment itself, but rather to hold the physical address. So again, we use the base not to point to the segment itself, but rather to hold the physical address of the page table of the segment. So instead of that holding, like the earlier virtual form, holding the physical address or the physical frame of we use the base not to point to the segment. So it's not to point to the last part or the previous version of the code or the last execution of the code, but rather to hold the actual physical address or to track the physical address of the page table of that segment. So it's kind of like a way to track where that the physical address of that page table. The bounce register is used to indicate the end of the page table instead of how long that allocation in physical address is. So, or how many pages or how many valid pages it has. So again, the end of the page table. So in that page table, it could provide how many valid pages it has, because again, the page table are used to track the allocated physical address for the process. Now here, we're just separating the three different code segments, such as code, heap, and stock. So let's do a simple example to clarify. Assume a 32-bit virtual address space with 4 kilobyte pages and an address space split into four segments. So again, let's do a simple 32-bit virtual address space with a 4 kilobyte pages and an address space split into 4 segments. So we'll only use 3 segments for this example, one for code, one for heap, and one for stock. To determine which segment an address refers to, we'll use the 2 bits of the address space. Let's assume 00 is the unused segment, with 01 for code. So here's the code, 01, 10 for the heap, and 11 for the stock. Thus, a virtual address look like this. In the hardware, assume that there are 3 base or bound pairs, one for each code, heap, and stock. When a process is running, the base register for each of these segments contains the physical address of a linear page table for that segment. So again, we have 3 linear page table, and we use the base register for each of this segment for that process in the linear page table. Thus, each process in the system now has 3 page tables or linear page table associated with it. On a context switch, the registers must be changed to reflect the location of the page tables of the newly running process. Again, on a context switch, these page registers or these registers must be changed to reflect the location of the page tables of the newly running process. Again, on a context switch, these registers must be changed to reflect the location of the page table of the newly running process. So since we have 3 segments, if we change the context, this location of the page table of this register, or the base, of course you will change the base and the bound register if you change the process. So that's what's being changed. On a TLB mesh, assuming the hardware managed TLB, where the hardware is responsible for handling TLB misses, the hardware uses the segment bits to determine which base and bounds pair to use. So again, in PTE, or page table entry, we discussed in the previous video, we already have this activated in a modern hardware. We're just gonna use this segment, activate this segment bits now to be able to do that context switch. So the hardware then takes the physical address therein and combines it with the VPN as follows to form the address of the page table entry. So again, On a TLB miss, assuming a hardware managed TLB, where the hardware is responsible for handling TLB misses, the hardware uses the segment bits to determine which base and bounce pair to use on a context switch. So, like a TLB missed, on a TLB miss as well. So this will change the base and bound register that the hardware use. So as you can see, SN equals the virtual address and segmast to SN underscore ship. The hardware then takes the physical address therein. The hardware will now take the physical address therein for that base and bound register and combines it with the VPN. So here, virtual address and VPN mask, VPN ship. So address of PTE equals to base SN plus VPN size of PTE. So it combines that with the that computation on the previous base and bound register and the new VPN being allocated, or the new process being created. This sequence should look familiar. It is virtually identical to what we saw before with linear page tables. The only difference, of course, is the use of one of 3 segment based registers instead of a single page table based register. So it's still the same with the linear page table. We just use the segment based register to utilize that on each segment to avoid this unallocated space. The critical difference in our hybrid scheme is the presence of bounce register per segment. Each bounce register holds the value of the maximum valid page in the segment. For example, if the code segment is using the first 3 pages, 0, 1, 2, the code segment page table will only have 3 entries allocated to it, and the bounce register will be set to 3. So the only difference here with the previous form or large table that we have that hasn't allocated is the bound register. So for example, the code segment has 0, 1, 2, 3. There will be this bound register that will be set to 3. That will be our that value will be our guide to be able to reduce this unallocated memory. Memory access beyond the end of the segment will generate an exception. So the code for this will generate an exception if you exceed or greater than this bounds register, and will likely lead to termination of the process. In this manner, our hybrid approach realizes a significant memory savings compared to linear page table. So again, it removed the unallocated space using this activating this SN for our base and bound register to track the base and bound register, and using an if else statement in our hybrid approach or code in our page data structure, our page table data structure, enormously have significant memory savings compared to the linear page table. Unallocated pages between the stock and the heap no longer take up space in page table. So the unallocated pages between the stock and the heap no longer take up space in a page table by marking them as invalid. So we just use an if else. If not valid, or if valid equals to false, therefore we just mark them unallocated in our code. So here's the graph again. It's the same as before. Valid, so we just mark 1, 1, 1, 1, and then all of this will be rejected. So this present, we will discuss that in the future video. We need this for converting memory to disk, on how the disk actually help the memory for those to make an illusion of multiple running process, or to make an illusion of a large memory. of the system. However, as you might notice, this approach is not without problems. First, it still requires us to use segmentation. As we discussed before, segmentation is not quite as flexible as pages. That's why we discussed the fixed size pages, because fixed size pages reduce the need for unallocated spaces or non-contiguous spaces. Reduce the problem of non-contiguous spaces when making a request as we would like, as it assumes a certain usage pattern of the address space. If we have a large but sparsely used heap, for example, we can still end up with a lot of page table waste. So it only assume certain usage patterns, such as using a code segment. But if we have a large but sparely used heap, however, if we have this it assumed that you use the heap as well. But for if most of your code does not use heap, or a lot of large size request without actually having the programmer allocate something in malloc, we will still end up a lot with page table waste, just like a big page table we encountered before. Second, this hybrid causes external fragmentation to rise again. So external fragmentation are what we encounter in segmentation. So we reduce the internal fragmentation, but the external fragmentation, the need to track the free list or the free elements, and then the need to have a contiguous space arise again. While most of memory is managed in page size units, page table now can be of arbitrary size in multiple of PDEs. So because just like in segmentation, yes, we have fixed units, we use page, but because most memory is managed in page size units, page tables now can be of arbitrary size. So we now change the characteristics of page table. We made it an arbitrary size, like in multiple of PTEs. Therefore, now instead of having the memory or external fragmentation problem outside of the pages, normal pages, we now have it in page table, because the page table size could vary. So we configure it to be able to change itself. So we will solve that later using multi-level page table. Thus, finding the phrase for them in memory is more complicated. Additional disadvantage is that it is complicated to just create an data structure and algorithm for this, and not all complication are better. If you don't need a complication that will help you achieve your goal, such as the performance, usually depending on your goal, then you just waste time creating that complication if it doesn't serve your goals. For this reason, people continued to look for better ways to implement smaller page tables.